So today we'll be starting with the earthquake size determinations. Okay, so that's our task today for the first hour. Let's see how much we can cover in the first hour. Uh, so so we after we got any earthquake, we the natural first question is always the size or the how big is this earthquake, right? So that we have to determine. And so there are two ways of determination. The earlier, before the instrumentation was implemented in 1930 or afterwards, that the the size was determined by the amount of destruction it has done. So that is basically what we call it as in nowadays, it's a maximum seismic intensity. So that way we always measure the earthquake, but we have found out that that method may not be always correct because intensity of the intensity scale are very much dependent on the point where you have observed or where the earthquake has occurred. So beyond that, it will be very difficult to estimate from the destruction caused. So so maximum intensity is still used. That scale is still used, but this is for some other purpose now. And we will touch upon that point during the time of the earthquake hazard analysis. We have the intensity measurement things which we all know. So that will be used there. That is now currently used there much accurately. But here we will be doing the size by estimating the magnitude. So intensity scale or the modified intensity scale, these are mostly outdated, and it does not have any seismometers or anything is involved or any instrument is involved for this measurement. And the third of all, it is a very subjective in nature, because how you felt a earthquake, that will be very difficult to, and that will be vary from one person to the other person, right? And also the amount of destruction is also depending upon the place to place and and all the construction practices and everything. So that will not be very accurate. The next part is the magnitude estimation. So magnitude estimation is a relatively modern method compared to the intensity, and we uses the seismometers. We will not say that it has no problem at all. It has problems, but the number of problems are much less than that used by the intensity scale. Okay. So first of all, let me show you the one cartoon, which is the maximum intensity earthquake. Is basically, if you use the size, then in the 1906 San Francisco earthquake in California region, so in that area, this intensity is almost the 7 to 8, but as it moves from the epicenter, the intensity value decreases, and that is obvious because the destruction will be much less. And so therefore you can understand that the depending upon the location, the intensity scale changes. So basically the maximum intensity is 7 in this case, but this is not a San Francisco. This is the Parkfield, sorry. But this is the Parkfield one. So 1966 Parkfield earthquake. So that's the destruction part. Okay. So that's their maximum intensity scale at the time. Now, if you compare the two earthquakes, this is what I was trying to say. The one is the 1906 San Francisco earthquake, and the other is 1811 or 12, the New Madrid earthquake in the central part of America. So you can see here, both of these earthquakes are of same size. Right? Their magnitude, if you can call it as a magnitude wise, they are of same size. But you can see the regions of San Francisco earthquake and the things or the felt things in the New Madrid earthquake was much bigger. Well, because it is located in a relatively hard rock, and this is your but outside of this relatively hard rock, but here it is a very soft sediment, so it attenuates very fast, and as a result, although they are of same size, the size, but their intensity felt in regions are different, right? So it will be very difficult to conclude from the intensity map that how or what is the difference between these two earthquakes. Okay, now, so we shifted towards the earthquake magnitude estimation. So if you can see that that the ground, if you are assuming that the ground is located on a or the ground is basically excited by a monochromatic seismic wave. So monochromatic means it has a single frequency or the energy source, and so the displacement of the ground, if you can call it as an xt, then that xt will be, if you assume that earthquake is a monochromatic things and it is basically the cosine function, so xt will be equals to a cosine 2 pi t by t, right? So that is your or x cos omega t, whatever you call it. So t is the time period. So that's the ground velocity will be equals to, then it is the minus 2 pi a sine 2 pi by t, right? So if you take the kinetic energy density, so that means it is basically half into rho into xt square. So that means this is the velocity square over a time period of t. If you can do that, then the kinetic energy density will be equals to rho into pi square a square by t square, right? So that's it. Well, if you can integrate it over the time period of this, so this is the rho pi square a square by t square. So the kinetic energy is basically it's basically 2 times of these values, right? So 2 EPAT. So if you can see this, that there is a mean potential of the kinetic and this one, so then it will be just the 2 times of this, including the potential and the kinetic part, right? So if you can calculate this seismic wave energy density at one location over a entire spherical wave front, okay, so then we can calculate our expression ES, or the energy, will be equals to F 4 pi. So this is a function, this is your distance, density, and this function, and a by t square. So that a by t square is coming here. So E is equals to the energy radiated by the source and the distance traveled. So if you can calculate or take the logarithm of both sides, then this log of ES will be equals to 2 log a by t plus log of some functions, right? So that's your these values. Right. Now, the point I like to make is this, that there is a function with your energy calculation, there is a function involved. This will be always equals to the a by t, so that the amplitude of the motion and the time period of the earthquake is involved in the energy estimations, right? Plus, there are some terms which is the which we need to compute, and that we basically use to calculate the ES, right? So we need to compute this FRPC, and it's a complicated term because that all depends upon how, what is the site location, how the regional correction factor, these are all involved there in that term. But this is directly, this energy is related to the log of AT, right? So this term is a measurable term. So we can measure this term, and if this amplitude and the time period of the wave is measured from the seismogram, so this is a good start to understand how we can use the magnitude as a parameter of measurement, and for amount of energy released from an earthquake, how can I calculate it, right? So that's your very basis of the magnitude estimations, right? So in 1930, there are two scientists. One is the Waditi from Japan and the Richter from California. They all basically try to formulate a scale by which we can calculate the magnitude of an earthquake or the size of an earthquake, right? So they simultaneously work on the peak amplitude. As I said, that this is basically, amplitude is the important factor. So peak amplitude of the seismogram and from the different events, and try to compute the energy release. And they understood that the peak amplitude decreases with the distance from the location of the earthquake, right? So let's first, it is the Richter who has formulated this scale, and so that is what we call it as a Richter scale, or the Richter magnitude, and sometimes it is also called local magnitude or ML scale. We'll come to that, but Richter has investigating the California earthquake. So he was only interested at the time in a Californian earthquake. So, and he has a seismogram, which is called Wood-Anderson seismic sensors. And these sensors are installed in a California area. And this is a particular type of instrument. And this is all standard instrument, and at the time, and that instrument was all over the California, and he was trying to get the amplitude data for different event from that instrumented response. So that means he just take the amplitude values, and he understood, or he has observed, that the amplitude value decreases with the distance. So that means the station to station, if you can plot all the amplitude value, then he said that it is decreases with the distances. Okay, and then he realized that we can calculate some magnitude or some numbers for a different type of earthquake, and that is where he was first proposed the scale. So earthquake magnitude scale therefore originated because of the desire for an objective measurement of earthquake sites, and also the development of the new equipment, which we call it as a seismometer, which is the Anderson seismometer. When Wood-Anderson seismometer comes in, and they had simultaneously Wood-Anderson seismometer and the Richter measurement actually created first the earthquake size. So if you can see, from the baseline, the maximum amplitude, whatever is the maximum amplitude they require, they calculate these peak amplitude values, and then this is your time, of course. So, but we are not interested. We are only interested in the maximum recorded things. And this can be done in a 3 different or 4 different station or with the distance. And then they calculate the this Richter or this magnitude, right? Now, so this is the first seismogram, which is basically we call it as a Wood-Anderson seismometer, and this seismometer is a relatively uh, relatively huge seismometer in compared to the towards our modern day seismometer size, and so they were trying to and these are all analog record. You can see that these are all analog on a smoke paper. These things are being recorded, and so he said, as per that law, that the magnitude equals to log A by T with some factors. This factor is dependent on the delta, which is the epicentral distance, and the H is the depth of the earthquake, and also some correction factor, CS and CR. So this CS is called the station correction. A stands for the station. So it's a stations correction because the different station has the different variability because of the amplification or the rock type things. And then he also introduced another term which is known as the regional corrections, right? So, but for him, the regional correction is not a very huge factor because he is only doing at the California part, and so. But if you try to apply that relation to some other part of the country, then you have to use the CR or the regional correction, and that is what mostly the different the earthquake agency, when they report the money, still nowadays when they report the local magnitude, they always use that your CR factor, which is different from the California to Alaska to Midwestern region to the eastern part. They are all different values, so that we have to put it as a correction factor, right? But please understand, this functional relation is a logarithmic relation. So the magnitude is in a log scale. So the log scale means a change in one magnitude unit is basically the 10 times improvement of the amplitude, right? So because this is a log base 10, so it is a log 10. So that is why it is a 10 times will be used as a one magnitude change, right? Okay. Now, the Richter actually uses at the different distances from the earthquake, right? So from the earthquake, he measured the distances and also the amplitude on that Wood-Anderson seismometer for a particular event. Now, if it is a zero distance, so he found out that the correction they need to apply is a 1.4. So this is your minus log A0. So that means assuming that the amplitude value, logarithmic amplitude at the zero distance is 1.4, and then he has given a scale with a 10, 20 different distances, it will have a different logarithmic values, right? So that you have to add in order to calculate the actual values of the magnitude, right? So the local magnitude ML will be equals to, therefore, log A and log A0 minus log A0. That will be equals to the ML. So basically the ML will be equals to the log of A divided by A0. So that means with a zero distance, you have to normalize it, right? So that value you have to calculate for a, say suppose A is a, with a Richter closest reference earthquake is ML0. So the ML0 is the reference earthquake. So magnitude ML equals to 0 is the basically the reference earthquake, and and that is minus 1.4. So if you calculate that, that will be equals to 10 to the power minus 6 meters. So that will be the values, and at an epicentral distance of 100 kilometers. So his formula, after modified it, so it's a log A. You can put the log A value and then minus 0.26 plus 1.65 log delta, where delta is basically 0 to 200 kilometers. And he also said that another 200 and beyond, we should use this formula by the different delta values, and log A will be equals to, so A you measured, I think the A will be measured in the millimeter scale, and then we can calculate the magnitude. And this is his, I cannot. So this is the scale, this is the actual observation he has made with a different earthquake, and this is your magnitude 2 earthquake, magnitude 3 earthquake, how it is decreases with the distance. All the amplitudes are decreases the distance. He plotted these values like this way. So basically we are measuring now magnitude values based on the seismometer. So ML magnitude is basically, we are using only the Wood-Anderson seismometer. So any ML, you cannot use it with the seismometer, whatever you have. So that will not be giving you the ML value. So ML value, you have to convert it back to the Wood-Anderson seismometer response, and that we can calculate after that, right? So similarly, if we have calculate the body wave magnitude MB, then it is a short period teleseismic P wave things. If we have a surface wave magnitude, then it will be the long period, and it is the teleseismic surface wave will be used. Then if it is a coda part of the earthquake, so if you can see that the coda means if it is a P wave, then there is a S wave, and then there is a surface waves. After surface waves, there is a long trail of this thing. So this is what we call it as the coda. So Aki and also afterwards few scientists, they had used the coda as a one of the reliable magnitude for a local earthquake. So this is your M coda. So but you have to calibrate it properly for your particular regions, right? But if you can, then the coda magnitude will be a very, very reliable estimations for till the, if it is not a very huge earthquake, right? So now, currently we are all using MW measurement. MW is the moment magnitude measurement. So this is based on physics. So there is nothing scale or instrument height. This is all the physics based earthquake estimation. So that is what we are using. The moment magnitude is nowadays is more scientifically accurate estimation of the magnitude than the other methods. And we will be coming to those points which we like to point it out, how to measure that. Okay. Now let's see, you have a seismometer in your place or in your observatory. So that has recorded a response, right, in an earthquake. So that's fine. But from here, you cannot take the amplitude values and can calculate the magnitude values or the ML value based on that. So what you need to do, you have to convert it to a Wood-Anderson seismic response for that one. So that means that is very easy to do in your any OBSPI or any type of things. You can calculate the Wood-Anderson response by giving your actual response from the seismometer and all your instrument parameter. If you give, then ask them to provide you the Wood-Anderson seismometer response for that, so that Wood-Anderson seismometer response will be available, and that can be used for your ML estimations, right? So this is what I told you earlier, that ML equals to amplitude of this earthquake particular and amplitude of a reference earthquake. And the reference earthquake values are all given on that table. So that is that you know, and then that is your reference amplitude values. So the reference amplitude means it's a 3.0 magnitude at a 1 millimeter distance, and it is at 100 kilometer depth, 100 kilometer distances, right? So ML will be equals to log A minus log A0. For the Southern California, Richter has suggested this relation, but please remember this relation is only for the Southern California earthquake, not for other regions. If you use it, you have to add some other correction factors, right? So log A minus 2.48 plus 2.76 into the log of distance. This distance is in kilometers. Good. So if I say that there is an earthquake, what I do first, I first calculate what is the distance, right? Because I have to give the distance value here. So, and I told you last time that if we can measure the TS minus TP distance, TS minus TP, then you can calculate the distance if you can divide by with 8. So basically the TS, so 8R will be equals to 8 into TS minus TP, right? So that is your distance calculation that you first do by taking the TS minus TP. So let's see at this point here, this is your TP. So TP equals to 1 second, and the TS, if you can identify here, so then TS equals to 6 seconds. So if I calculate TS minus TP equals to 5 into 8, so that means this earthquake is at a 40 kilometer from the site, right? So that's the first thing, that it is a 40 kilometer from the site that we have established. Now we need to calculate the magnitude of an earthquake. Okay, now in order to do that, that your distance versus log A0, if you can plot, that plot is also looks like this way. So that means if you do not like to see the tabular data, if you like to see the graphical results, so this is your log A by distance formula. Now, if you convert that response, as I said it to earlier, that to a Wood-Anderson seismic response, and then you calculate the peak amplitude from here. So let's see, this value is coming here, and we can calculate this value is around 828. I calculated earlier, so 828 in between. So the distance is 10. So then we have to see that the table to calculate log A0 values. So let's go back to calculate log A0 here. I think, yeah. So at 40, the log A0 equals to 2.4, right? So this is the minus log A0. So you understand that minus log A0 is already given as a 2.4. So you can put that.
Yes.
So log A minus log A0. So log A0 is minus 2.4. So you can put it. So log A equals to 828. So log 828 plus 2.4. So if you can take that, this is the 2.9 plus 2.4. So that means it's a magnitude equals to 5.3. So that's, you can calculate directly by seeing a saying a record, only you need to be understood that whenever you are recording it, you need to know that instrument parameters, particularly its time period values, because Wood Anderson seismometer has a 2800 is the, I have the numbers here. Okay. So this has a 2800 is their magnifications, and 0.8 second is the period. So you have to have you need to know that your instrument magnification as well as the period, and then that value you need to incorporate into your parameters, and then give the Wood Anderson will be automatically set, and they will be giving you they first deconvolve your results from that magnification, and then multiplying with the Wood Anderson seismometer response, and then calculate the Wood Anderson response values, right? So that will be giving you the magnitude calculations. Is it okay? So it is observed that if you have a strong motion accelerogram record, then the strong motion accelerogram record more or less matches with the Wood Anderson seismometer, because they are basically principles are the same. So sometimes if you have a proper near about magnification things, the strong motion accelerogram record can be directly used for the Wood Anderson, because that response will not be that much of big difference, right? So now currently the ML, the Richter magnitude, is not being used. Although if you see the report from any earthquake has occurred in the press or in the TV, they will first say it's the Richter magnitude scale, this magnitude is this much, because they never modified it. So they always say it's a Richter magnitude, but the Richter magnitude scale are not mostly reported, because all the agencies are mostly gives the either the MB or MS or the moment magnitude, but whatever magnitude is given, so they all convert it to the press always convert it to the Richter magnitude, because they know that the Richter magnitude is the magnitude of the earthquake. But this is not the case. Okay, so Richter magnitude is abused by the press a lot. But the Richter magnitude requires the Wood Anderson seismometer. Without Wood Anderson seismometer, which is not present nowadays in anywhere, except in one of the museum in California, they have still the Wood Anderson seismometer, and some of the observatory they still keep the Wood Anderson seismometer. But beside that, there is no Wood Anderson seismometer is in place for the active recording, right? So therefore, ML scale does not make any sense. But IUGG, the International Union of Geology and Geophysics, has standardized a ML scale formula, and that formula they used is this one. This is ML will be equals to log a 1.11 log R plus, this is the 0.91 plus 0.00189 into log of the distance, into the distance, multiply the distance, and then 0.91 as a correction factor. So they use the R as a hypocentral distance, is basically delta square plus H square. So this is your hypocentral distance, not the epicentral distance. So it is a hypocentral distance. Please remember that. And typically it is a less than 1,000 kilometers we use, and H is in the depth in kilometer. And the amplitude is measured in a micron. So that means 10 to the power minus 6. So please, whenever you are using the IUGG formula, be careful about your unit values, right? So it has to be expressed in a microns. It has to be hypocentral distance, and then we can use that. and we are basically try to measure from the horizontal component, right? So these are the three things you should keep it in mind whenever you are trying to report the ML scale as per the IUGG formula, which is your standard. We call it as a standard formula, ISPI, and the International Union of Geodesy and Geophysics. They are basically gives this formula. Now, the what are the shortcoming of the ML scale? The instrument the wood Anderson were used are very narrow band and basically single dominant period of 0.8 second, and the seismicity was for the shallow earthquake, more or less 15 kilometer deep. If it is a deeper earthquake, the ML scale is not totally usable. But fortunately for the California, since the earthquakes are very shallow, so therefore Richter is a little bit lucky whenever he was trying to give this relation, because he has fortunately taken all the shallow earthquakes, right? And it is Wood Anderson seismogram is basically uncommon nowadays, and it will be very difficult to use this scale for our daily reporting, right? Okay, so it has not been used for a long time by any professional things. So now the modern seismology or the modern seismologists are using the other two different scale. There's one scale we call it as a body wave magnitude scale, and other scale is known as a surface wave magnitude scale. So we call it as a MB, and there is a MS. Okay, so these are the two scale. One is the body wave, and other is the surface wave magnitude scale. Now, and these are done with the teleseismic waves. So not the local things. For the teleseismic wave, it can be calculated very nicely. So MB, if you can measure, we can measure it here, right? So MB will be measured at the body wave side when the wave just arrived at the recording station, which is the body wave part of the things, and then the MS will be used in those part, which is the surface wave part. As I told you, this is your body wave, means it's a P wave arrival, then there is a S wave arrival, and then there is a surface wave. So in the surface wave, we measure it here, and we call it as basically the Rayleigh wave part. And the Rayleigh wave can be, we can get it from which component? From which component we can calculate the Rayleigh wave?
Fast.
Huh?
What? Which is to provide and lead working in a daddy.
Huh?
It's called working in an area though.
Particle component. So it's basically the particle component we use for the Rayleigh wave computations. So we will see the particle component, and we can find out the Rayleigh wave resulted from the particle component, right? Okay. Now, first of all, let's see the body wave part. So body wave magnitude is basically the MB, right? So this MB is measured from the distance on the teleseismic earthquake, and we are using the wave or the period which is basically the 5 second to 20 second, right? So basically it will be the 5 second like this to say 20 second like this. Okay, so this is your 5 second time period. So we take the 5 second time period, the maximum amplitude, and or might be the 20 second time period. So any time period between the 5 to 20 second, if you can reliably measure that amplitude, you can take that, right? And this can be either P wave or PP wave or the S wave, right? So we can use that three wave. So basically P, PP, and S. And you remember the P means it's basically the wave which is arrive directly from the earthquake source, right? And then the PP which is basically basically being reflected two times because it's a teleseismic wave. So if it is reflected two times, so that's a PP wave. So PP is the uh, so that phase we can use and we can uh, measure the maximum velocity because we are using the broadband. So MB for a broadband station is equals to log of V max by 2 pi plus a factor, which is your distance factor. So this is your Q, H, and delta. So H is the depth and delta is the distance or the epicentral distance in H, epicentral distance, right? So that we can use to calculate the broadband. From the broadband data, which is the velocity sensors, you calculate maximum velocity divided by 2 pi, and that you can use for the body wave magnitude calculations, right? So the body of magnitude in the ISPI or the Indian International Association of Seismic and Planetary Earth Interiors. So they have a 2011. They had given a formula for MB estimation. Now please remember this is your MB. That is your the body wave magnitude, but not being from the broadband station. So this is a log of A by T plus Q into H delta. So A is the ground motion amplitude in micrometers, right? So this is in a micrometers. That means it's a displacement values, and T is the period in second. Okay, so in general, they measure the MB in a period of less than 3 seconds. So please understand, these are the two different formula. This is using directly the broadband velocity sensors data, and this is only the displacement values log A, because this is in a micrometer, so 10 to the power minus 6 or the micron, and T is in a period in second. And in practice, we use this one as a less than 3 seconds, right? And the QH delta T is again the correction factors, right? So, so as I try to tell you that there are different ways of measurement, and there are different process of measurements, and some of the measurement values are not unique. So that means if you measure some by some assumption, and I measure the some assumption, the MB might vary, okay, because of the formula we have used. But that's the beauty, and that is what the magnitude scale by using this seismometer type of response is a little bit not unique numbers. Okay, so next is there is another way of measuring the body wave magnitude, that is called from the LG wave. So LG wave is basically the particular type of shear wave, which is basically have a velocity in this range, okay, 3.2 to 3.6. So this is the group speed of this shear wave with a group speed of roughly in the range of 3.2 to 3.6 kilometer. And LG is a mixture of energy from the and if you can use that LG signal, you have to first identify the LG signal from in the seismometer. That can be done if you have a lot of stations in the nearby, then you can easily calculate the group, the signal between 3.2 f to 3.6, and then that will be the your LG signal. And if you can use the LG signal, then MBLG, the USGS. So this relation is a US Geological Survey relation. So they use this relation as their MB calculation based on LG. So this will be between 0.5 to 0.4 degree. So 0.5 means it's a something around 55 kilometer to 450 kilometer distance. So that's that distance. You can use that MBLG if you have any earthquake like this with the S wave velocity at 3.2 to 3.6, then you can do. And if you have a larger distance, teleseismic, of course, so this will be the 450 kilometers to something around 3,000 kilometers you can use. Okay, 3,300 kilometers you can use. So this is also is in a micron, and time period is in second. And please remember here the delta is in degree. So delta, whatever delta value you have to give, it will be always, you have to give it in degree. So whenever you are using the formula for computing that, please give a careful look about the unit, whatever you need to do. So the ISPy has given another formula. So that is the USGS formula, but the ISPy formula is like this, log 10A, and this is also in a nanometer. This A value, here it is a nanometer, and this nanometer is basically, we have a say suppose, let's see, this is a wave train from the 3.6 kilometer per second to 3.2 kilometer per second, right? So this is a wave signal comes like this, right? So this will be you have to choose the third largest amplitude in this time window. So whatever is the third largest, so that you need to choose. Okay, so that will be equals to your A values, and then you can calculate between 3.6 to 3.2 kilometer time period. The arrival time with a T, or the T is ranges between in between this one. So that you measure first the time period of this H wave, you can measure the time period, and this time period has to be 0.7 second to 1.3. Any value in between will be fine. And then we have to use the third largest amplitude and calculate the R is the epicentral distance in kilometer, and this is your there is a gamma values. There's gamma is a coefficient of attenuation in kilometer inverse. So that value, I think the gamma value is basically this gamma value is equals to pi divided by q into u into t, where u is the group velocity, which is the 3.6 to 3.2, whatever you are using. T is the time period, whatever time period you have used, and we can calculate this. Right, there is a chart available for the P wave in a vertical component, P wave in a horizontal component, and the PP wave in a vertical component, PP wave in a horizontal component, and all the delta values, different degree values. So these are the Q. This your gamma that you have to use for these numbers, right? So depending upon your distance, you choose whatever the P wave in the vertical component are you measuring, or horizontal component you are measuring. So you put that gamma value based on that, right? So this is your distance and this is the depth. When there is a depth connection at different depth, we have a different depth connection from the 0 to 800 kilometer depth. So that values we can use for this gamma, and then it will be a the gamma, the MB by LG, right? So that's the way of calculating MB, and we will be taking in your tutorial section, we will be analyzing some of the magnitude calculation based on this formula, and you will see how they will be different, although it is the same earthquake, but the different formula can produce a different type of numbers for the MB, right? MB or MS, whatever is this. Now, so if it is a more than 600 kilometer distance, okay, if the beyond the 600 kilometers distance, the long period seismogram for the shallow earthquake are dominated by the surface wave. As I told you that if it is a shallow earthquake, then the surface wave is a very important factor, and we need to see that effect. And last class I had shown in the California how severe or how big is the surface wave effect for a very local earthquake, right? So basically, this surface wave, we are interested to calculate a 20-second time period. So that means whenever you see that this value has to be 20 seconds or near about 20 seconds. Okay, so we take the corresponding amplitude of the 20-second time period of the surface wave in order to calculate the surface wave magnitude. So this is what we call it MS-20 measurement. So whenever you see the seismogram, you find out in your surface wave, is there any 20-second amplitude? So the 20-second, if it is a 20-second in the time, then you find out what is the maximum amplitude, and that value you put it here, t equals to 20 seconds, and then you can put this number delta you have already calculated by the S and P distance, and then you can use this formula to this one. But again, please you remember that this is all log A by T. That's the part is basically the basis of the magnitude calculations, right? So these things are from the vertical component because it's a Rayleigh wave things, vertical component, and in between the delta is from the 20 to 160 kilometer. But this is not always the case, but it's fine. The 20 to 160 kilometer means it's a 2,000 to 16,000 kilometer for the long distance, the surface waves, right? And then surface wave can also be calculated from the broadband seismometer, and that will be equals to, so in that case, the Vmax divided by 2 pi, all other things will be all same. But this can be used for any period between 3 to 6 and 60 seconds. If you use the broadband data, then the period can be 3 seconds to 600 seconds, and you can apply from the 200 kilometer to 1600 kilometers. But please remember, this is the velocity, and this is the maximum absolute down velocity, right? And this is a microns per second. So this is microns per second type of values, right? So this is directly the velocity recorded on a broadband seismometer that you can use with a period of 3 seconds to 60 seconds, any number, and the maximum things you can, or maximum amplitude, you can use whatever you can get it in between this gel, and it could be any epicentral distance from the two to this one. Right? So that's your broadband. I told you the broadband, if it is not a if it is not a broadband station, then we can use this formula. If it is a broadband station, we can use this formula, and each one has a different way of measurement, so that you should respect that and compute the surface wave magnitudes. Right? Now, let's see one earthquake happens, and you have recorded MB, you have recorded MH from the surface wave, from the body wave part, you have recorded the MB values. For the surface wave, you compute the MS waves or the MS values. And ideally, we should expect this value to be same, right? Because this is a one earthquake, and if I have to report now, how should I report? If it is not same, then it is a very difficult to report, right? But often you will see that they are not same numbers. So ideally, we want there has to be MS will be equals to the MB will be equals to the ML, but it never be the case. Okay, it mostly they are all different things. In Turkey earthquake in 1999, it's a big Turkey earthquake. The MS value was 7.8, but the MB value equals to 6.3. Right, so that's a order of magnitude difference, right? So this Taiwan, they have this relation from the 1999 a Taiwan earthquake. We also have a MS equals to 7.7, MB equals to 6.6, right? So this says that MB and MS, whatever we have learned so far, although we can report it, but it will not be the same. Now, why they are not same? Why they are not same? The first thing is this, that these numbers are basically based on some of the observed record, right? And there is nothing physics is involved here, or nothing rule is involved here. So basically, whatever you are observing, based on that, you are trying to give a numbers. But that number or the amplitude or anything, that depends upon a lot of other factors. Factor means how the stations is located, which type of soil it has been located, how far this station from the epicenter zones. So these are all other the factors, and that will affect the recorded values. Okay, so we may not get that same, because this is based on some empirical observed or the basically the recorded observed data. So we will not get the same number. We should not get the same numbers, right? So this distance from the correction for the amplitude, this depends on the geology. So if it is a one rock type and you have applied a distance correction, now a different rock type may not have the same distance correction. So if you have used a uniform distance correction for all the station, that will hampers the actual the numbers, right? So basically and the second of all, if it is a very deep earthquake, then as I told you last time, that the surface wave may not exist. So basically, the predicting the MS waves or MS magnitude based on a deeper earthquake is a wrong idea, right? So So therefore, another observations which we like to do or like to understand, that the magnitude scale saturates. The magnitude scale gets saturated. Saturated means after certain magnitude, when even if the earthquake is bigger, the magnitude values remains the same. And that magnitude is around 6.5 body magnitude. So if you see there is a magnitude value written 6.5, then you should have a doubt on that magnitude numbers, because it might be a bigger earthquake, but it's still in the body wave, it will give you 6.6. So if you see a 6.6, then you need to see what will be the MS scale values, because that will not reflect the actual thing. So a 7.7 magnitude earthquake can give 6.6. A 8.2 magnitude earthquake, the body wave magnitude can be 6.6. Right? So that does not indicate that the change of the size of the earthquake. We'll come to the next one.